Being exposed to radiation, ionizing radiation from an X-ray tube, to have a look at your bones, is an example of irradiation. That when a current passes between here, X-rays pass through my body, and that is that. When the current is switched off and this machine is taken away, I am not myself radioactive. I have just been exposed to radioactivity. Irradiation is only dangerous whilst I'm here, being exposed to this source of radiation. But there is another kind of exposure that in some circumstances might be far worse. Here on the Roof of Science we have a long-standing experiment of rainwater collection. Here are funnels rainwater here. Why? Well, we're looking to see if uncontrolled releases of radiation have contaminated our atmosphere. When the Chernobyl nuclear disaster occurred, one of the first ways in which the wider world knew about it was because of contaminated rainwater falling in countries that was downwind of the accident. What we do is we collect the rainwater and we analyse how much radiation it is carrying to see if there are contaminants in that water. Now, this use of the word contamination, it is different to irradiation. You see, this water, if contaminated with radiation, has radioactive particles within it, and these unstable nuclei are going to give off radiation. If I was to drink this, then those radioactive nuclei are going to be in me, and I would be contaminated. In a sense, I would be a walking, talking radiation source. This contaminated water I might not drink, but it might be taken up by plants that I might eat. And so again, it gets into the food chain. Contamination is bad because once you are contaminated, you can't get away from the source of radiation because it's you. You are the source of the radiation in that case. Here I have a cloud chamber. I've got a small piece of pitch blende inside here, and I've got two active, interesting things going on. First of all, this is a refrigerator, so it's cooling down the air inside here. And I've got a few drops of propantuol, or isopropanol, that's forming a vapour inside this chamber. Now what's happening is the alpha particles being emitted from the pitch blende are becoming visible as they travel through the chamber. Seeing those vapour trails is evidence of ionization of the propantuol. That big, heavy, charged particle charging through is actually having an effect of disturbing the electron configuration of this. Now, that can also happen with you. It's the main danger of radiation is that it could ionize the molecules inside your cells. The problem with that comes with this. Your genetic code is carried on a molecule found inside your cells. If any part of your DNA was ionized, then it might change the code of what it reads, leading to such conditions as mutations, sterilization of the cell, might even cause cancer. As a medical doctor, I might be exposed to a lot of radiation. For example, the ionizing radiation that is used in an X-ray, or radiotherapy, which uses gamma rays, and other uses of radiation in medicine. The patient might only be exposed to radiation for a very short amount of time, but me, the doctor, by having multiple patients, I'm exposed again and again and again. So the first thing that affects the total amount of dose I receive is, in fact, the amount of time I spend with the radioactive substance. Another thing is this. Come with me. Come on. Aha. You see right here we're much closer to the source of radiation. In fact, this is light, visible light, and so not ionizing. But in the same way, if we were closer to the source of the ionizing radiation, that would result in us having a greater dose. There's one final thing that we can do to reduce the dose that we are exposed to, alongside reducing the time and increasing the distance. It is this. We could put a screen between the source of radiation and ourselves, you see dentists and people that do x-rays standing behind a screen or stepping outside of the door. Key thing though, how would I know how much radiation I have been exposed to over the course of perhaps a year? Does it exceed the recommended guidelines? Well, I'm wearing a film badge. Inside this plastic thing is a piece of photographic film, which, when radiation falls on it, exposes it and makes it change colour. It has different windows. Some windows are completely exposed, others are behind a layer of aluminium and lead to see what type of radiation I've been exposed to. You see, gamma rays will expose all three of the different windows, whereas alpha particles will only go through the window that has the thinnest screen. So what I can do is I can actually look at which radioactive particles or radiation I've encountered and then look at the effect that that's going to have on my body. Alpha particles are not a great danger if you're irradiated by them, but in contamination, if they get inside myself by drinking things contaminated with alpha particles, or indeed eating anything or breathing in dust that contains alpha particles, then this is going to be very bad for me. However, I'm more likely to be damaged by radiation if it is something like beta particles or very strong gamma rays. All of these things have to be taken into consideration when working with radiation. We must treat radiation with respect, because if we get it wrong, well, it leads to very serious health conditions such as cancers and other terrible diseases. But that's not to say that radiation is bad. As Madame Curie said, it is to be understood, not feared. And through that understanding, we've been able to find many practical applications of nuclear radiation. Have you ever wondered how a smoke alarm works? Inside a smoke alarm, there are two main things. One is a buzzer to make a noise if there is smoke detected. But there's something very interesting here. It's actually a use of nuclear radiation that we use to detect smoke. To understand how it works, I have this exploded version of a smoke detector. What I have is two things: an alpha particle source and an alpha particle detector. And between them, there is a really small air gap. Now, what I'm going to do is I'm going to record how many alpha particles are being detected on this counter over the space of about 2 minutes. Then we're going to repeat the experiment, but we're going to use this smoke machine to fill this room with smoke to see if the detected amount of alpha particles is less. The theory goes that the smoke in the air gap is actually going to provide larger particles for the alpha particles to be absorbed by, so that not all of them reach the detector. Well, let's give it a go. (624). 624 counts of alpha particles when no smoke is present. So now we're going to repeat the experiment with a constant source of smoke being produced by this smoke machine for 2 minutes, and we hope we don't set off the smoke alarms in the building. What's the worst that can happen? Well, let's have a go. So the smoke machine, it didn't go off for as long as the 2-minute integration. But one thing that it did do was, in that time, it accounted for many, many fewer instances of radiation. The actual activity rate was at about 0.47, whereas before, the activity rate was more like 5.2. So my detector, if it was triggered to go off, if the activity went below a certain value, then it would detect the smoke in this room. And so this is a really great use of radiation. Because the smoke will absorb the alpha particles, it doesn't get to the detector, and so therefore will trigger the alarm. Let's just hope it doesn't trigger the alarm in here. If I had a leaking pipe, it might be obvious where the leak is because the water might be showing up at the surface. But what if it's not showing up at the surface? What do we do? Well, what we can do is we can put radioactive substance into the water passing through the pipe. where that water then leaks out into the ground beyond the view of our eyes, then what we would find is an accumulation of radioactive material. So what you would do is you'd go along with your Geiger counter to the point where it starts to pick up an excess of radiation. That's where you need to dig, because that is where the leak is. The use of radioactivity to find leaks in pipes. Another really inventive use of nuclear radiation is in a paper mill. Here we've got a model of what is going on. A source, in this case of light, but in the paper mill it would be beta radiation, is shining through the paper, and a detector is placed to measure the amount of detected beta particles on this side. Now they do this so that what happens is that if the paper is too thick, the beta particles start to get absorbed, and in that case a computer sends information through the rollers to squeeze the paper more, making it thinner. If more beta particles are detected, the paper's too thin and the rollers are told to move apart. So let's see how this works. So let's have a look. What we can see is this meter here is showing 0.28, and this indicates how many beta particles are getting through the paper. As the paper is pulled through the rollers, we can see that it's fairly constant. But then, oh no, a slightly thicker piece of paper is coming along. The wood pulp must have been thicker or something, but either way, what has been now detected is that the amount of beta particles has gone much less, which means that the two rollers have, by computer, moved closer together to squash the paper thinner again. And so after a short interval, the paper has corrected itself and is now at the correct thickness once more. And you can see it's back to 0.28. That's how paper is made uniformly thick, all because of nuclear radiation. I'm injecting myself with a radioactive isotope of iodine. You see, this here is going to go around my entire blood system, and it's going to be detectable on the outside, because this iodine is going to give off gamma rays. And we know from the penetrative properties of gamma rays that they can actually travel through material. They can be detected on the outside of my body. So I can see everywhere where this radioactive tracer has gone. I can check to see that my circulatory system is working well, or I can treat an area of my body by sending a radioactive substance to that area, what we know of as radiotherapy. I could have it intravenously, like this, or alternatively, I could drink it. But either way, radiation in medicine is a very, very useful tool. This material, I would have to particularly select the isotope. So that one, it was a gamma emitter, but two, that it had a short half-life. I need it to have a short half-life so it doesn't linger in my body for too long. It needs to be in my body for long enough so that the doctors can measure it, but then it needs to decay and stop being radioactive as quick as possible. It's been a couple of hours since I've had this radioactive tracer put into my body. You can see that now this gamma camera can detect the gamma rays coming from the radioactive material in my bloodstream. It helps me to identify whether or not there is a problem, whether or not there is blood flow in this finger, for example. Now this will wear off in just a few hours because we've selected a substance with a short half-life.